Yeah. So hello, everyone. Welcome to the ICTS Colloquium. It's a pleasure to have Divyang Bhimani today give the talk. So I'll go ahead and introduce our speaker. Divyang got his PhD from HRI, working under Professor Ratnakumar on modulation spaces and nonlinear evolution equations. After that, he has been a postdoc at TFR CAM and is currently an inspired faculty member there. He's also had some research experience and visits elsewhere during this time. So he was the Indo-US SERB Research Fellow at the Norbert Wiener Center for Harmonic Analysis at University of Maryland. And he was then a Lebesgue postdoc fellow at Rennes in France. So his main areas of interest are harmonic analysis and PDEs. And today he's going to talk about modulation spaces and applications to Hartree-Fock equations. So Divyang, over to you.
Thank you, Vishal, for the introduction. And thank you very much for this opportunity to giving me a talk here. So today I will talk about modulation spaces and applications to Hartree-Fock equations. So I will talk the related topics in this talk. So modulation spaces and Wiener amalgam spaces and the composition operators. And I will also talk about a little bit Hermite multipliers. And then we shall talk how these are connected to Hartree-Fock equations and its a local and global well-posedness results. Now to start my talk, I will tell you first why I was interested in studying modulation spaces and what are its connection to nonlinear Schrodinger equation and Hartree-Fock equations. So to do that, I will start with notations. These are the standard notations. So this is a Schwartz class function known as a rapidly decaying functions, tempered distribution. These are just the notations I'm going to use, the Fourier transform and the inverse Fourier transforms throughout my talk. So now to motivate, I will motivate the talk. I will start with the nonlinear Schrodinger equation. So the nonlinear Schrodinger equation is I delta t u x t plus Laplacian u of xt equal to f of u. So here f represents the nonlinearity and this delta is the standard Laplacian. So this is known as a Schrodinger equation. Now let's start with the free Schrodinger equation. This means we start with f equal to 0 and then we see what is happening. So to motivate why we are interested in modulation spaces, we start with the free Schrodinger equation. So this is a free Schrodinger equation. That means I am taking without any nonlinearity. Here I'm taking 0. And let's take the Fourier transform throughout. Let's see what is the solution of this equation. So let's take the Fourier transform throughout. If we take the Fourier transform throughout, then we know that the Fourier transform take the Laplacian to the polynomial time itself. So this is, we end up getting this ODE. So this is the simple ODE del t of u hat of xi t equal to minus 4 pi square I mod xi square u hat of xi t. So
sorry, can I ask one quick question?
Sure.
Sorry, I'm not exactly familiar with this notation on a day-to-day basis.
Yeah,
can
sure.
you please go back and remind what the difference between f cap and f, so to say, this lower hat? Yeah.
No, this is the inverse Fourier transform. So here the only difference you can see is a minus and here you will have a plus.
Okay, but you started with a function f. So
yeah.
F hat is its Fourier transform.
Yeah.
And now what is f? I don't know what to call it. F
inverse Fourier transform. This is inverse Fourier transform basically.
Okay.
Yeah.
Okay. Yeah.
So this is the inverse Fourier transform.
Yeah. Okay. Fine.
Yeah. Thank you. So yeah. So here if we take the inverse Fourier transform throughout. So if we take the inverse Fourier transform throughout, then we have u hat of xi t equal to, this is now a simple ODE, and by the separation of variable we can solve this ODE using this initial condition. And then we have u hat of xi t equal to e to the power minus 4 pi I square t mod xi square u naught hat of xi. So this is basically what we have is the solution in the Fourier transform side. We have a modulated exponential time u naught hat of xi. So we have I here. Therefore, we have a modulated exponential time this. And then if we take the inverse Fourier transform, because we want the solution back in the space variable, so we take the inverse Fourier transform. So if we take the inverse Fourier transform, so we have a e to the power minus it for pi square. So basically we are taking the inverse Fourier transform, and we know that the Fourier transform takes the pointwise multiplication to the convolution. So we will get this. So basically inverse Fourier transform of, so here we will get e to the power minus it for pi square. So this is basically now the kernel of our free Schrodinger equation, the inverse Fourier transform of this symbol. And this is just the notation again, e to the power it delta u naught. So whenever we write this will represent the solution of the free Schrodinger equation. So now we ask a very simple question. Okay, so this is formally we have solved a free Schrodinger equation. If we start with initial data u naught in L2, can we say the solution uxt is also in L2? That's our question. So so L2, we know that it's the square integrable functions. And can we say that the solution is also in L2? The answer is yes, because let's try to compute the L2 norm of the solution. If we compute the L2 norm of the solution, then this is nothing but the inverse Fourier transform of this quantity. But we know that by Plancherel theorem, it preserves the Fourier transform. So basically, it preserves the Fourier transform. So basically, L2 norm is the same as this quantity. And this is the modulated exponential. So when we take the modulus, it will not create any issue. So we come back to the u naught hat of L2. We again apply the Plancherel theorem, and we have u naught of L2 norm. So what we have is now the solution of free Schrodinger equation of L2 norm is exactly the L2 norm of the initial data. So that means we can solve the free Schrodinger equation in L2 norm. Whenever we have this norm is finite, the solution is also in L2. So now it is a natural question is, okay, we can solve this free Schrodinger equation in L2. Can we solve this free Schrodinger equation in LP spaces? So now, before answering that question, let me remark here that, so this is, as we have seen, that it preserves the Fourier transform. The free Schrodinger propagator preserves the Fourier transform. So we have the exactly L2 norm. And let's compute the L infinity norm. So this is, we have seen that the free Schrodinger equation, we remember that this is, we can write as a convolution of this, and this is some kernel. And we want to compute the L infinity norm, but then we know that the L infinity, L1 convolution, L infinity is a subset of L infinity. So we end up computing the, by Young's inequality, L infinity norm of this. And here we required some computation, but then we can compute its inverse Fourier transform. And if you take its L infinity norm, we end up getting 1 upon t to the power d by 2 f of L1 norm. So now here what is important thing is we have a Schrodinger propagator which is a linear, and now we have seen that it is a bounded operator from L2 to L2, and it is also a bounded operator from L1 to L infinity. And then we can do a Ries-Thorin interpolation theorem. We can play with the Ries-Thorin interpolation theorem, and then we can get the estimate between 2 and infinity and 1 and 2. So we will get basically LP prime estimate. So what we have is now e to the power it delta LP prime is less than or equal to this time. Here we required some work to show that, but it's just the application of Ries-Thorin interpolation. And then what we have is we have this LP prime estimate. So we have t to the power minus d by 2, 1 upon p minus 1 upon p prime. And we can see here that at near t equal to 0, we have a singularity. As time goes to 0, we have a singularity. So that creates a problem. And as t tends to infinity, we have a nice decay. And using this is called a dispersive estimate for the free Schrodinger propagator. And using this estimate, actually, we can show that this Schrodinger propagator maps from LP to LP if and only if p equal to y. So this is very easy to see once we have this estimate. Why? Because if possible, let's assume that the Schrodinger propagator maps from LP to LP for p greater than 2. That means we have this estimate. E to the power it delta f LP is less than or equal to f of LP for p greater than 2. And now we can choose f in LP, which is, let's say, some large norm is not non-zero and some large number, and then this is just by definition. We can apply the definition and we can write f as a e to the power it delta, apply on e to the power minus it delta of f, and then we take the LP norm, but then we apply our assumption, whatever we have assumed for p greater than 2, this is bounded, so we have this estimate, and then here we apply this dispersive estimate, so we will get the LP prime of this. Now we can see that as t tends to infinity, this part goes to 0, but this side we have assumed it is large, so this is definitely a contradiction. That means this propagator maps from LP to LP for p greater than 2 is not possible, and using duality we can also show that between 1 less than 2 and 1 it is not possible. So now we have observed that now the Schrodinger propagator maps from LP to LP if and only if p equal to 2. So this asks a natural question. Okay, we cannot solve a free Schrodinger equation in the LP spaces for p not equal to 2 only, but can we find another Banach space where we can solve a free Schrodinger equation? Because then we can put a nonlinearity and try to study it's the solution of the nonlinear Schrodinger equation. So that's the question. Okay, can we find a Banach space so we can solve this Schrodinger equation? And or we can ask, so basically what is this? This is a convolution operator. More generally, this is a convolution operator with the symbol e to the power it mod xi to the power alpha. So when alpha equal to 2, it is exactly the Schrodinger equation, the case which we have seen. So more generally, we can also ask a question, okay, can we say the Fourier multiplier, which is defined as M Chuck convolution F, where M is the Fourier multiplier, and can we say this Fourier multiplier is bounded on the space X to itself? So this becomes the harmonic analysis questions, and people are interested to study whether this multiplier is bounded on the space X to X. And in particular cases, let's say when alpha equal to 2, as we have seen, it gives the solution to free Schrodinger equation. Alpha equal to 1 case also appears in the wave equation, if you are familiar. Okay, so this question. The next question is, can we erase the singularity at origin? As we have observed in the previous slide that in LP to LP prime, we have a singularity at origin, but can we find a Banach space so which we do not have a singularity at origin and we have a nice
question?
Yeah, sure.
About this point about singularity at the origin, yeah. I'm really confused. Maybe you explained it. It's the inequality on the right hand side. So what if it goes to infinity?
No, I'm saying here at your time goes to 0, you have a singularity.
But that doesn't mean the solution blows up. That's on the right hand side.
No, that's fine. That's fine. I'm saying that doesn't mean anything. I'm saying, can we improve this estimate? Because this estimate is used to get local and global well-posedness results.
So you want a tighter estimate?
Yeah. Can we improve this estimate? Because when we study a global well-posedness, this estimate play a very important role.
Agreed. The other point, when you say you want to find a Banach space, I assume you're not happy with HK type Hilbert spaces.
No, that is fine. HS is fine, but these are again L2 based Hilbert space, right? We want which is something beyond p not equal to 2.
But I can get an algebra on HS as well.
Yeah, that's fine. That's fine. For S greater than d by 2 or some indices on S, we have the algebra.
Okay. All right.
That's fine. But I mean, the problem with HS is, maybe I will tell you later, there are some in the supercritical regime, still we have an issue with the nonlinear Schrodinger equation.
Okay.
Okay, so should I go ahead?
Yeah, please.
Yeah, oh, thanks. All right, so now the question is, can we find a Banach space so we can solve the free Schrodinger equation? All right, so and we shall see that the modulation spaces answer this question nicely. So to define a modulation spaces, let me introduce first short time Fourier transform. So what is a short time Fourier transform? So short time Fourier transform is short time Fourier transform, the short time Fourier transform of f with respect to the window function, which is coming from the Schwartz class, is integration f of t g of t minus x e to the power minus 2 pi I w dot t dt. So here we see that we have a two variable, the space variable and the frequency variable. And let's try to understand, if we just don't have g of t, then it is just nothing but the Fourier transform. And we can also think of as, let's say g is just something like one, like a bump function. So we have one here, and then it is 0, and then we are just translating. So then what it tells that short Fourier transform is nothing but the Fourier transform of f, of the segment of f locally. And then when x varies toward the x-axis, the window also varies towards the x-axis. It takes the different positions, and therefore it is also known as the sliding window Fourier transform. And also we can introduce the notation. So let's say if we have use this notation, translation and modulation operator. So we can rewrite this as MWTX of G, and when G is in Schwartz class function, we can also show that this time frequency shift is also in Schwartz class, and therefore also we can think of as this temper distribution acting on Schwartz class function. And now what is the idea of modulation spaces? So here basically this is the short Fourier transform. We have the space variable and frequency variable. So when we define the LP spaces, we have only, we compute, basically we measure only the integrability with respect to the space variable, but here we compute, we wants to measure the space variable and the frequency variable simultaneously. So how we can do that? We just put the integrability condition with respect to the space variable and frequency variable simultaneously. So how? So this is the definition of modulation spaces. So this is the short Fourier transform we have just defined in the previous slide. Also it is, I have written here. And then we take the LP norm with respect to the space variable first, and then we take the LQ norm with respect to the frequency variable, and then we also put this weight. So and then when we say this norm is finite, we can say that this is a member of the f is a member of modulation spaces. So this is the definition of modulation spaces, and we can also show that if we have a two different window function, g1 not equal to g2, then we can show that this definition is equivalent. Norm of the definition is equivalent. And also there is the equivalent definition of the modulation spaces. So how? So it is, let's say we have a bump function which is 1 in small interval and then 0 outside, which has to be smooth, but then it is 0 eventually. And then what we do, let's take the translation of this this function rho, and then we just translate it by that. So this is a compactly supported function. The support will remain the same for even for the translation. It just changes, but the size of the support will remain same. And then we define the rho k. So rho k will be just, we wants to take some summation of rho k is 1, so we divide by this summation of L in Z, rho L and rho k. And then we decomposed RD as so this is the unit cube, and we can decompose RD as a cube. And as we have observed here, the support of rho k is subset of this, and the size of support of this will be uniform, because we are just translating. We are starting with the compactly supported function, and then we are just translating. And using this also we can define a modulation spaces. How? So we have to define a frequency decomposition operator. So what is a frequency decomposition operator? So rho k, which we have defined in the previous slide, just we take some compactly supported function and we translate it f hat and then its inverse Fourier transform. So we can see that on the Fourier side it has the same structure, localized same structure, because rho k is essentially have the same structure. So it is known as a frequency uniform decomposition operator. And then we can take f hat of rho k and its inverse Fourier transform LP. So then we take the LP norm first, and then we have a discrete variable, so we take the little LQ norm. And then we can generate the spaces, and we can show that this definition is equivalent to the modulation spaces. And the one more remark is, if we change the order of integration, when p equal to q, it will be the same, but for p not equal to q, we get another family of spaces, which is known as a Wiener amalgam spaces. And if we are familiar with the Bezow spaces, in the Bezow spaces, what we do is, we are not translating by just integers, but then in that case, we have this xi upon 2 to the power k. We take the scaling of the function xi, let's say some function gamma, and then we take gamma upon xi upon 2 to the power k. So there the support will not be the uniform. The support will have a psi is 2 to the power k. And using this type of operator, we have basically dyadic decomposition operator. And using this operator, we can generate the spaces, which is known as a Bezow spaces. All right, so this is about definition of modulation spaces. And I will tell you now quickly some properties of the modulation spaces. So what are the properties of the modulation spaces? So for P, see, we know that LP is not an algebra under pointwise multiplication. For when we have the second indexed one, MP1 is the algebra under pointwise multiplication. And also we can show that it is closed under complex conjugation. So when we have this type of nonlinearity, f mod f to the power 2k, so we have this nice estimate, f to the power 2k plus 1 MP1 of s, so which we will use later in our study. And also by now we have relations known between which the classical spaces like LP and other spaces, and when it will subset of modulation spaces and so on. Another important property is the Fourier transform preserves the Fourier transform. In the case of LP, we know that only L2 preserves the L2 space preserves the Fourier transform. But in the case of modulation spaces, MPP for all p between 1 and infinity preserves the Fourier transform. So I can quickly tell you the proof of this fact. The proof of this proving algebra property is quite technical. So I can quickly tell you, just to give a flavor, why these spaces are interesting and why it preserves the Fourier transform. Let me again recall the short Fourier transform. So this is what the short Fourier transform we have defined. We can play with the Plancherel theorem, and we can do a little bit of algebra, and we can rewrite this actually as a short Fourier transform as V g hat f hat w minus x. So this is very, very important property, because we can just observe that this time frequency, it relates basically the f, it relates the f and f hat. It relates, this short Fourier transform relates f and its Fourier transform. And what it does is, it just, roughly speaking, it just switches the time frequency shift xw by w minus x by 90 degree. And therefore, what is the definition of modulation spaces? We have to take the LP norm throughout. So if we now take the LP norm, it is clear from this first inequality, the second equality, that it preserves the MPP norm. So that's the advantage to working with this space. We have, it preserves the MPP norm. It preserves the Fourier transform norm. And then also we can do a little bit algebra here, and we can rewrite this in terms of the convolution form. So again, the short Fourier transform we can rewrite as f convolution mw of g star of x by taking this exponential quantity outside. And once we have this, so now we have a very nice form of short time Fourier transform. We can rewrite STFT in terms of the convolution. And this really helps us to compute, let's say we have in LP space Young's type inequality. So f convolution h, when f is in LP and h is in LQ, then f convolution h is in LR for some relations between P, Q, and R. So here now, if you want to have that kind of relation, so then let's take, we compute f convolution h. We want to have this type of relations in modulation spaces. So let's compute f convolution h. So what is f convolution h? So I'm just putting here f convolution h here. And then as we have note that it is independent of the choice of window function. So I can take two window function, G0, convolution 0, both are in Schwartz class. And then MW of G star convolution MW of G star, and then I can split. So I can get F convolution MW of G star convolution H convolution MW of G star. So basically now short Fourier transform of the convolution of two function is again we can write as a convolution of two function. And then we want to have like Young's type inequality in modulation spaces. So what we do is we apply now LP Young's inequality with respect to the space variable. So we can apply Young's inequality. Then we have LP norm of this into LQ norm of this, and that is will depend on the function of this xi variable, and then we can apply the Holder's inequality. So what we get is this type of algebra property. So this is essentially because of algebra property relation, 1 upon P1 plus 1 upon P2 equal to 1 plus 1 upon P0. That's coming because of Young's inequality, and this coming because of the Holder's inequality. And in the modulation spaces, we get this type of relationship. And here we may ask why we are talking about here algebra property. Then we recall Schrodinger propagator. So what was our Schrodinger propagator? Our Schrodinger propagator was also nothing but the convolution operator. So the Schrodinger propagator is also the convolution operator. So we have the convolution operator. And then obviously we are interested in computing this. And then we can apply the MPQ. Then obviously we can apply this type of algebra property, and we want the second indices also PQ. Then this becomes 1 infinity. So now our job is to compute basically this M1 infinity norm of this symbol, and with sigma t is e to the power I pi t mod xi square, which appears as the solution symbol of the free Schrodinger equation. And also we can show that the inverse Fourier transform of this, we can write this as a Wiener amalgam space of this. Then we end up computing the Wiener amalgam space norm of the sigma t, where sigma t is e to the power I pi t mod xi square. Now again, to compute this, we have to compute the short Fourier transform of this. So I will quickly tell you how we can do that. So this I'm skipping a little technical details. So this is the symbol sigma t we are interested in here to computing the short Fourier transform of this, and we are fixing some window function g equal to e to the power minus pi mod xi square, and then we can rewrite basically as a generalized Fourier generalized Gaussian, and it is available that how to compute the Fourier transform of the generalized Gaussian, and using the operators we have defined time translation and modulation, we can rewrite this generalization Fourier transform of generalized Gaussian in this form, and then by taking the modulus we end up getting this. And so once we have this form, and then we can have to just take the L1 norm, and then with respect to then the supremum with respect to that, so we have compute basically the computing the sigma w infinity norm of the sigma t, which is the Fourier multiplier. So we have this t square plus 1 to the power d by 4 with some little bit of computation. And but what as a byproduct of this we got is we got now when alpha equal to 2, e to the power I, the Schrodinger propagator maps from MPQ to MPQ. So this is the result. We have sketched the proof for alpha equal to 2. And we have observed that in LP to LP, it was the map only for P equal to 2, but it is bounded on MPQ for all PQ. So this is the advantage here we have. So we can now solve the free Schrodinger equation on modulation spaces. So this was basically proved for alpha equal to 2 using the frequency decomposition technique. But here the proof I have present is using time frequency analysis. And that time, these people, Ruzhansky-Sugimoto-Wang and his collaborator from the Peking University, they were not knowing even that this is actually the modulation spaces. Their paper was inspired by the Bezout spaces, and here they do the frequency decomposition and prove the result for alpha equal to 2. And the later people have proved this result for general multiplier when alpha is not equal to 2, but when alpha is in 0 to 2. And also for that, the result is proved in the consequent in the later paper. And then later people have studied when alpha greater than 2, but then we don't have the exact estimate. We have some loss of regularity. All right, so here now we have proved that free Schrodinger equation we can solve in modulation spaces. Now let's take the nonlinearity and let's see what happened. So let's take now, we have now a Schrodinger equation, and we take the nonlinearity of the form mod u to the power 2 ku. So when f is mod z to the power 2k z, then basically this nonlinearity becomes u to the power 2 ku. And then we start with initial data in MP1, and then we have also the solution in MP1. So this is the result proved earlier. It was proved for p equal to 2, and then later people have generalized for p not equal to 2. So here the important point is here, for instance, the MP1 we can embed in LP, and it is a sharp embedding. And even today we cannot solve NLS with let's say initial data in L infinity, and we have the solution also in L infinity for the nonlinear Schrodinger equation. But the question here, we can solve in MP1, we can solve the NLS in MP1, and in particular in M infinity 1, which is a subset of L infinity. So this is the importance of this result. And here I can tell you the quick sketch of the proof. So basically the idea of the proof is we rewrite the solution equation in the form of Duhamel's formulation. And so this is basically e to the power minus it delta of u0 minus I 0 to t into this non-homogeneous part. And then we reduce the argument to the fixed point theorem, Banach contraction principle, but then we have to control this free part and this nonlinear part. So how we can control the free part? So to control the free part, we have proved that it is uniformly bounded on MPQ. So we have now e to the power minus it delta u0 MPQ is less than or equal to some time dependency into u0 of MPQ. And for the controlling the nonlinearity, we have u to the power 2ku, as we have observed that MP1 is an algebra, and therefore we have this type of estimate. Now combining these two estimate, it is then very easy to compute, show that this has a fixed point using a Banach contraction principle in this appropriate ball in C0T of MP1 of RD. And this basically gives the local well-posedness results in the modulation spaces for MP1 result. And then the next question here is, okay, why 2K only? See here, f of z, here we are taking the nonlinearity z to the power 2kz. Why not 2k plus 1? So that's the question we can ask. Why not other nonlinearity? So there was a question left open by, there is a group of people from Imperial College London, Ruzhansky, and from Nagoya University, Sugimoto, and Peking University, Wang. So these are the group of people came together, and they raised this as an open question. Okay, we have the estimate for when alpha belongs to 2n, but what happen when can we have this type of estimate? Does mod u to the power alpha u MP1 norm is less than or equal to u to the power MP1 norm of alpha plus 1 holds for every alpha in 0 to infinity minus 2n. So why this problem is important? Because this was at the intersection of various equations, not only in the Schrodinger equation, but various other equations as well. And if we can solve this, then we have the local well-posedness results as a first step. So this was the question left open by the experts in this field of research. And we have been trying to understand this problem and trying how to prove this estimate. And then we end up studying a composition operator. So what is the composition operator then? So we were investigating this question, and then we end up studying composition operator. So I will define what is a composition operator. So the composition operator is, let's say, we start with f from C to C function, and then we define TF of f equal to f composed f. So f is basically RD to C, and then you have f from C to C. So this makes sense. F composed f equal to f of x. And it is easy to see that TF composition operator are simple examples of nonlinear mappings, because we can take f of z equal to, for instance, z to the power pz, then this is nothing but becomes mod f to the power pf, as we have seen the nonlinearity in the previous slide. So we have been studying this problem, and we proved the following theorem, which says that for the given f, for any given f from R2 to C or C to C, and we have the composition operator maps from M11 to M11 if and only if f of 0 is 0 and f is real analytic on R2. So we have completely understood the nonlinear map composition operators in the case of M11. And for p greater than 1, we have a one-way result. If composition operator maps from MP1 to itself, then we have f is real analytic on R2. So this is the result we have proved. And I'm not going into the proof of this result, but what I will tell you is what is the connection of this result with the previous estimate. So as an application of this result, we can conclude that there exists f in MP1. There exists f is in MP1 such that f into mod f to the power alpha is not in MP1 for any alpha in 0 infinity minus 2n. So we start with f equal to, suppose if it is possible, let's assume that f is of the form z to the power z mod z to the power alpha, and alpha is in this range. And if assume that TF maps from MP1 to MP1, that means f composed f belongs to MP1 for every f in MP1, then f has to be real analytic by previous theorem. But here we can easily show that when alpha is here, f is not going to be real analytic, and therefore it gives a contradiction. That means whatever here we are saying, if possible, this is true, that is no more true. And therefore there exists f is in MP1 such that f into mod f to the power alpha is not in MP1. And therefore what we have concluded is, as a consequence of our theorem, we could answer the negatively to the open question raised by Ruzhansky-Sugimoto and Wang that this estimate is not suitable. So this estimate we cannot expect because there exists u in MP1 such that u mod u to the power alpha is not in MP1. Also, we can, let me make here side remark, as an application of the previous theorem, we can show that there exists f is in MP1 so that modulus of f is not in MP1. And this makes
Divyang, question?
Yeah, sure, please.
So you answered it negatively in the case of MP1.
Yeah.
What about MPQ though?
Actually the question, I mean the knowledge of composition operator on modulation spaces is very limited actually. Right now we do not know. I mean, it's right now we understood only on MP1, and with some weight there is a recent paper in 2020. So it's not very clear how function operates in these spaces.
Okay. Is there any reason to expect that the inequality might hold for MPQ?
Oh, well, maybe it will. I mean, I see the proof of our theorem. Basically, we could make the analysis locally, and locally it coincides with the Fourier algebra.
Right.
And in the Fourier algebra, in the case of MP1, definitely we could not. I mean, it's very delicate. So maybe for the smooth function, putting some weight we might expect. I'm not sure about without weight.
I see. On a related note, your original local well-posedness was in continuous functions from time into MP1.
Yes. Perfect.
Even if the initial data is in MPQ.
Not MP1. Last indexed I want 1, because otherwise we can't use this estimate, and then it creates a problem to get the fixed point argument, run the fixed point argument.
Right. So the local well-posedness is only true in MP1 so far.
Yeah, MP1 so far.
Okay.
Yeah.
Okay. Thanks.
And just one note I wanted to make here, for instance, as we have observed, the spaces are very delicate. F is in MP1. then modulus of f may not be an MP1. So we cannot just take simply modulus inside when we are trying to prove some estimates. So that makes life little difficult. Okay, so this is what we have observed is, we have observed now NLS so far is locally well-posed in MP1, but standard approach as people are using in the spaces is rule out when we have the nonlinearity, which is not smooth. And but then, okay, question is, can we say what about the global well-posedness? Whatever we have proved the local well-posedness in MP1, can we extend that solution to the global in time? That's the another question. And that question was answered for the small data. If you start with small initial data, then basically in the you can have the global existence in M21, and M21 basically contains, let's say, HS Sobolev space for s greater than d by 2, so we can control the initial data which is beyond HS. Okay, so the global well-posedness for the small data was there, and I have just cited one, and then there has been so many papers appears in this direction. But what was left open was, can we have the global well-posedness for the large initial data? That means there is no any initial conditions on the initial data, and still can you have the global existence results? So that was the question for the global existence, and by the same researcher, it has been raised this as an open question, and this is still remains open question since last around 15 years, whether can we have, if you take initial data in M21 and still you have NLS is globally well-posed in modulation space. So this is an open question. So I have been trying to understand why we are unable to get the global well-posedness result here, and we end up studying, and I end up studying the Hartree equation. So Hartree equation here is, I will define now Hartree equation. So Hartree equation is basically, it's a Schrodinger equation, but the nonlinearity here we have now is not a power type, but k convolution mod u square u. And this k is also known as a Hartree kernel when gamma equal to 1, also known as a Coulomb potential. So 1 upon mod x to the power gamma. And here I am, okay, this is a fractional Laplacian. So fractional Laplacian I am defining using a Fourier transform. So Fourier transform of this fractional Laplacian is basically mod z to the power alpha Fourier transform of u. So when alpha equal to 2, it coincides with the standard Laplacian. So this is the Hartree equation, and for the Hartree equation, this it goes back to the 1975 with Chadam and Glacy. They essentially proved some results in H1 in dimension 3, and here I was interested in studying this equation in modulation spaces. And what the result here we put, very first result here we got is, let's take initial data in MPQ. So here there is no second indexed 1. Let's take initial data in MPQ, and when alpha equal to 2, that is the standard Laplacian, then there exists a unique global solution of this point 1 is Hartree equation. Hartree equation, U belongs to C of R MPQ, and this some regularity. This comes because of some Strichartz estimate. I will tell you later. So this is the first result appears in this realm of modulation spaces, which deals with the global existence without any smallness assumption on the initial data. And when we don't have standard Laplacian, that times we need to assume a radiality assumption on the initial data. If we start with initial data to be radial, and then for the higher dimension, d greater than or equal to 2, and for this range of alpha, we have again a unique global solution for the fractional Hartree equation in the modulation spaces. So this is the result about the Hartree equation. And later on, we have studied the Hartree-Fock equation. So I will tell you now what is a Hartree-Fock equation. So Hartree-Fock equation is the system of equations, and here we have the system of equations. So I delta t psi k minus of delta to the power alpha by 2 psi k and 1 to n And this is basically Hartree nonlinearity, and this is known as the exchange term or the Fock term. And the Hartree-Fock equations of finite particles, basically this is, and the same question we can ask here, whether we start with initial data in modulation spaces, and can we have again the solution in the modulation spaces. So the many people have been studying this equation, Hartree-Fock equation. For instance, there is a paper in Communication in Mathematical Physics where they proved that finite time blow-up solutions in H1/2 norm by Lenzman and Froelich. So here, what is our contribution for this equation? So this is a, okay, so I will tell you now result. So for this technical assumption on the index that gamma, which is coming from the Hartree nonlinearity, 0 less than gamma less than minimum of alpha d by 2, and then one of the following statement holds. So MPQ, then we need to have a restriction. 1 is less than equal to P less than equal to 2, and the restriction on Q is 1 is less than equal to Q less than 2D upon 2 plus gamma. So this restriction is basically coming because of the trilinear estimate we have to prove in this for the Hartree type nonlinearity, and similarly this restrictions comes because of in MP1 of S we have to prove a trilinear estimate for the Hartree type nonlinearity. So this is a space X, and when I want to take non-radial, when fractional case, then time we have to take the radial assumption. So I'm taking the X to be this. So basically this RAD means all those functions which are radial. So radial assumption. And the first result we have proved in this direction is, okay, we start with initial data in the modulation spaces. So Xn, as we have defined here, modulation spaces. And these are some technical conditions on the spaces. So then there exists a unique global solution of the Hartree-Fock equation, so that psi1, psi2 up to psi n belongs to this spaces. And yeah, so X is a modulation spaces. So again, we have a global well-posedness result in the Hartree-Fock equations in the modulation spaces. And for the single Hartree equation, we have not covered this endpoint case. Here we are also covering this endpoint case 2D upon D plus gamma. Okay, so now I will tell you the idea of the proof of this result, and then I will talk about Hermite multipliers. All right. So I guess I have some time, right? Thanks.
Yeah, you have like
yeah, okay. Sorry?
You have about 6 or 7 minutes.
Oh, okay, fine. Thanks. So so this is local well-posedness. So like local well-posedness results. So basically local well-posedness. Okay, so the idea of the proof here is, let me I'll go a little fast. So idea of the local, so this is what is the idea of extending basically local well-posedness to the global well-posedness. So this is a local well-posedness. So for the local well-posedness, we do not need any radial assumption. And these are the technical conditions on the spaces. And again, the idea here is we rewrite the solution in terms of the Duhamel formulation. We have the trilinear, we have to prove the trilinear estimates and the uniform bound for e to the power minus it of minus delta to the power alpha by 2. Yeah, so this is the trilinear estimate we need to prove to handle the situation. To run the fixed point argument, we need to prove a trilinear estimate. And so this is a technical part. I'm not going into the proof of this result. And then we have to prove this fractional version of to handle the free Schrodinger part. So this is alpha equal to 2 case. We have seen the proof earlier. For alpha not equal to 2, this proof is little more involved, and it requires some oscillatory integral techniques. Oscillatory integral techniques, it requires to handle the situation when alpha is not equal to 2. And once we have this 2 estimate, we can handle the free part and the non-homogeneous part. And then again, the idea is to get the fixed point argument. So we have a Banach, we can choose a Banach space, and we can basically choose the Banach space, and then we can choose a small t positive, so that basically t will depend only on the initial data. and then we have a local well-posedness results in MPQ for the Hartree-Fock equation. And then now question is how to extend the local solution to the global in time. To extend the local solution to the global in time, the idea of the proof is we have now proved the local well-posedness in Xn in the modulation spaces, and then what we do is we prove the local well-posedness for the Hartree-Fock equation in the L2, and then we prove the Hartree-Fock equation local well-posedness, global well-posedness in the L2. Then we prove the we define this the maximal time of existence for the maximal time for the local solution, and then we prove this blow-up alternative. That means if t plus is finite, then we have this t tends to t plus, this is infinite, and then at the last step we show that this is basically the growth term remain the finite. So for any psi k in 0 to t x intersection L2, and we can show that for any t in 0 to t star, this remains finite, and then we can combine this the boundedness of growth term and this blow-up alternative to conclude that the solution is global in time. And so basically let me tell you what type of L2 well-posedness we need. So to prove the L2 global existence, we need a Strichartz estimate. So Strichartz estimate is basically control this now free part and non-homogeneous part. These are some technical conditions, and the radial assumptions comes because of a Strichartz estimate. Whenever we have U0 and F is radial, we have the Strichartz estimate, but when alpha equal to 2, we do not need a Strichartz estimate. So once we have a Strichartz estimate, we can use the Strichartz estimate to basically prove a global existence in L2. So these are the global existence result in L2, and the solution for any alpha fractional admissible pair Q and R, which is some conditions on Q and R. This is a fractional admissible pair. The solution will remain in LQ-LR locally. And basically now we use this global existence in L2 to conclude that this is the blow-up alternative, as we have this growth term remains finite. So this is the idea of the proof, to prove a global existence result in the modulation spaces. And from here actually some more restrictions comes on 0 less than gamma less than minimum of alpha less than d by 2. Yeah. To conclude this, to conclude that this growth term remains finite. And later on in the joint work with Saikatul Haq, we have also proved that this Hartree-Fock equation in LP intersection L2, but here we have the solution in the sense of twisted well-posedness result. So we transform the solution by the free Schrodinger operator, and then we have the well-posedness results. But here the ideas of the proof is a little different to get the local existence. As we have observed, the free Schrodinger operator will not map from LP to LP. All right, and then I will just take a couple of minutes to say a few words about this harmonic oscillator. So these are the results we have proved for the Laplacian without any potential. But now we can also consider the same Schrodinger equation with respect to minus delta plus mod x square. This is also known as a Hermite operator, also known as a quantum harmonic oscillator. And okay, and then this is the Fourier multiplier. So Fourier multiplier, in fact, we have already talked. So Tm of f is m f hat of Chuck, and then this is the problem in harmonic analysis. Under what condition on m? This operator Tm of f is bounded on MP LP to LP, and these are the famous results by Marcinkiewicz, Mikhlin, and Hormander. Is a picture of them. It says that under certain decay conditions on mj in the derivative condition on the multiplier, we have basically the Fourier multiplier is bounded on LP to LP for 1 less than p less than infinity. So this is the result. And okay, and now we wanted to study the similar result for the Hermite operator. So I will tell you. So this is the Hermite operator, and we have the Hermite operator, and phi alpha is the Hermite function, and 2 mod alpha plus d phi alpha. and these are the Hermite functions forms an orthonormal basis for the L2 of RD. This is known, and once we have an orthonormal basis, we can write F as a Hermite as a Hermite expansion F phi alpha, and then we can define for M, which is a bounded function, MH of F equal to M 2 mod alpha D F phi alpha. And then again, the question here is under what condition on M you can have the boundedness on Hermite multiplier on LP to LP. And this goes back to the result of Thangavelu, a very early result in 1987, his PhD thesis. Basically this is the discrete analog of that continuous result proved by Marcinkiewicz and Hormander, which says that if the difference has this decay, then we have MH is bounded on LP for 1 less than P less than infinity. And what I just wanted to mention here is we get exactly similar result on the modulation spaces. So this is the very similar condition as we have discussed in the case of LP multiplier, that we have under some condition on M, we have this operator MH is bounded on MPQ to MPQ, and this P greater than 2, our class is much larger than LP. So we have this Hormander type theorem is proved in a much larger class than LP. And we have also proved for a particular symbol sine t h to the power 1/2, h to the power 1/2 minus 1/2. And this basically gives the solution to the wave equation associated to minus delta plus mod x square. So we can also solve the wave equation associated to minus delta plus mod x square in the modulation spaces under the certain conditions on P and Q. And let's come back to the Schrodinger equation, which is we are focusing on this talk. So this equation we can write as a Schrodinger propagator e to the power it 2 mod alpha plus d f phi alpha. This is essentially basically the solution of the Schrodinger equation associated to minus delta plus mod x square. And for this, the result we have proved is it preserves the MPP norm for all P. So once we have this result, and then we have developed a similar tool like Strichartz estimates and global existence in L2. And then the growth term remains finite, even with when we added the minus delta plus mod x square term. Yeah, so then finally we have proved this result. So even if we add minus delta plus mod x square term in the Hartree-Fock equation, we can get the global existence. And in this previous result play a very important role, because this take care of the free part to the Schrodinger equation, and then we have a global wellposedness for the Hartree-Fock equation. Even we have minus delta plus mod x square. And yeah, here I will stop. Thank you.
Okay, thank you so much, Divyang. So I'll open the floor up for questions. If anyone has any questions, please go ahead. I see Rukmini.
Yeah, I had a question.
Yeah,
so,
sure,
you're proving well-posedness.
Yeah.
Does that mean in finite time it doesn't blow up? The solution doesn't blow up? Is that
No.
well-posedness?
No, I mean, it depends. For local, see, the local wellposedness we have proved that for that we cannot say anything. So we have proved a global wellposedness. For that, the finite time blow up will not occur.
Okay, but you don't get solutions this way, or do you also get the solutions?
No, we have a solution here. We have a solution means in the weak sense it satisfies a Duhamel's formulation.
But the explicit solution you can get, like, what I am asking the following: nonlinear Schrodinger, is in one dimension, it's an integrable systems.
Okay.
Right? And Zakharat-Sabat methods of inverse scattering transformation and all those things. They have actually found solutions, actual solutions.
Okay.
So what I'm asking is, what is the difference between your perspective and their perspective? You know what I mean?
Okay. I mean here we have for the Schrodinger equation, I think we have an explicit solution. Only thing is we are proving in existence, we are proving in the species which has, in roughly speaking, low regularity, rough initial data.
I see, I see. Rough initial data, you still have
Yeah,
solution.
so basically, I mean, we can embed the Sobolev spaces in modulation spaces. So these are bigger spaces. Still, we have global existence results here.
Oh, I see. Okay, okay.
Maybe I can add one comment.
Sure.
Which, Rukmini, in order to get
Yes.
Inverse scattering to work, you have to be in very particular spaces. The initial data has to belong to a very particular space.
Yeah,
There is, it's a weighted L1 type space, I believe, for Schrodinger equation.
I see.
So the kind of spaces that Divyang is talking about, I don't think you can even characterize the spectral data for the inverse scattering transform.
I see. Oh, okay. I see.
Yeah, and I would, but on the other hand, I would say that the notion of solution that inverse scattering transform gives you is a little more constructive, but it is also limited to integrable equations, and nothing Divyang mentioned needed integrability.
Right. But are there conserved quantities?
No, in terms of modulation spaces, no.
I see.
No, that's actually biggest problem here. Therefore, we are unable to say anything about global well-posedness in M21.
So maybe, can I ask a question?
Yeah, sure.
So just a follow-up to that. So since, so by the way, I'm not an expert in the area. So this I'm asking as a, and I think many people in the audience are probably not, some are not even mathematicians. So just to give you some context to the question. So out of, in functional analysis, there's a whole zoo of spaces, right? I can work with Banach spaces, Hilbert spaces, Fréchet spaces, nuclear vector spaces, bonological spaces. There's a whole lot of things I can work with. And you started with this thing about L2, which is, has a long history, of course, because Hilbert space occurs in quantum mechanics and so on. And from there, you went to saying you wanted to generalize it to some Banach space initially. And then at some point, you motivated working with modulation spaces because they behave well with respect to the fast Fourier transform.
Yeah,
if I understood correctly.
It gives a solution to Schrodinger equation.
Sure. So, but out of all the, all the kinds of spaces that exist out there, why should I be interested specifically in having initial data in these classes of spaces that you considered? I mean, what does it teach us more broadly about, about the Schrodinger equation, or even more generally about nonlinear PDEs? Is there some reason to look at this?
Okay, so for instance, this spaces has also other history from the time frequency analysis point of view. But from the NLS point of view, for instance, we can talk about in the terms of the Sobolev spaces, we can talk about its critical indexed. So for instance, if U is also a solution, then we can do the scaling U of lambda x and lambda square t is also a solution of the Schrodinger equation, multiplying by some lambda. And then so far, I mean, so in the critical index, so basically when the solution preserves that norm, we will say that index is a critical. And in the critical setup, and then beyond that, that is we call a subcritical. So that is well understood, but in the subcritical regime, supercritical, it is not, I mean, it's still, we haven't understood the solution of the Schrodinger equation well. And modulation spaces contains a data which was beyond that of that supercritical regime. So that was the motivation for the people here to started with. That was the one motivation, yeah.
But why is it this particular class of space? I mean, there's lots of kinds of things you can do in functional analysis. So how would you come up with, why do you look at initial data in these?
Okay, so for instance, let's say a Bezow spaces. Bezow spaces, for instance, for all P and Q, we cannot expect the Schrodinger propagator maps from Bezow spaces to itself. But here we can get it, the solutions. I mean, we start with the initial data in MPQ, and the solution is also in MPQ, which was not the case in Bezow spaces.
Mhm.
So I mean,
So I guess the question is, I mean, other than that, is there any motivation like to look into this initial data in these spaces?
so apart from that, yeah, I think this was the main motivation from this NLS and this nonlinear equations point of view. Apart from that, I don't know how to think about it.
Are there any other questions? So I just had one question. We've already talked quite a bit about your work before, but I just had one question.
Yeah, sure.
In order to get global well-posedness, you used the known results of global well-posedness in L2 spaces.
No, that we have proved actually. So I mean, our tools were known, but that result essentially we have formulated and proved as we needed in our setup.
I see. But in particular, did you have to show that the solution you get in NPQ space is actually the same solution you get in the L2 base space?
Yeah, it will be the same.
It is the same. Okay.
Yeah, it will be the same. Yeah.
Okay.
Yeah.
And I know in standard L2 theory, there is a persistence of regularity type result you can prove.
Yeah.
Can I prove similar things for NPQ?
I think so.
What does regularity mean, I guess, in NPQ? Is that the weight?
Yeah, weight indexed.
The weight index, I see.
Yeah.
Okay. And are there known embeddings into CK type spaces?
I think there are many results actually. I think by now there are so many papers which gives the embeddings between the classical spaces, all Sobolev and modulation spaces. So yeah, I think it is available.
So a but you didn't show any persistence of regularity result.
No, I mean I mean in my case I just needed to show that growth term is bounded. And what the regularity we are getting is just because of the Strichartz estimate.
Got it. Okay. Okay. All right. Yeah.
So can I ask a question?
Yeah, sure.
Yeah. So the uniqueness issue, have you thought about in NLS?
Yeah.
Is there like what are the kinds of solutions and
no, here we will get a uniqueness because of Banach contraction principle.
Oh, I see. Okay.
Banach.
Okay. So the solution is unique.
Yeah, solution.
Okay.
You can also probably prove uniqueness via Gronwall's type argument, right?
Yeah.
I mean, you are in a mild form anyway, so
Yeah.
that would be a natural thing to do.
Mm-hmm.
And is there a result that mild type solutions are the same as weak solutions?
No, there are a lot of activities going on, but I have to look at it. I mean, there are, because as you have pointed out, why not only second index is 1?
Yes.
So people have proved some mild solutions in that index, not
Right.
the one which I'm talking here.
Right.
Yeah.
Okay.
Can I ask another question?
Yeah, go ahead.
So it's broadly in the same spirit as my other question, but maybe I'll word it differently, sort of position it differently. So, where is this sort of leading? Like, what would you like to understand in the longer run about, say, the Schrodinger equation? I mean, it's of course very interesting that you have the space in which the equation is well posed and so on. But, is there a bigger thing that this is sort of building towards or leading to? Are you trying to understand something, some phenomenon that you would like to better understand, and this is a tool on the way, or is this the an end in itself? I mean, just to show
No,
that.
actually, for instance, well-posedness theory here in itself is we have a very limited knowledge, because only few cases we could consider. Another thing is here we have considered Hartree-Fock equations with only finitely many terms.
Mm-hmm.
So here basically we have the system with the only finitely many terms, and there are a couple of mathematical activity going on where you consider basically when you have infinitely many terms. So that part hopefully I would like to consider in future. So this is one thing, and of course many well-posedness results even in the modulation spaces case is not known. Yeah.
These badly behaved initial, the U-zeros, so do they arise in quantum mechanics? What I mean is U0 in your modulation spaces,
Okay.
do they arise in quantum mechanics?
Can I maybe interpret the question?
Yeah, sure.
Rukmini, is the question these rough initial data?
Okay.
Do they arise in application?
Exactly.
Is that the question?
Exactly. Yeah.
Oh, okay. Okay. So I mean, I don't know. I have to think about it exactly if it is appear or not. But right now, it is very active field of research for people who are doing this well-posedness business. To considering, you start with rough initial data. I mean, which is not very smooth, and still you want to have a solution. Yeah.
So I guess there are two things, right? I mean, nonlinear terms tend to produce roughness. When you have nonlinearity, you generate higher frequencies, which makes you, in some sense, rougher. So you produce roughness automatically when you have nonlinear equations.
Okay.
But I guess the main question with roughness is probably criticality and role of critical index.
Yeah.
That people want to understand supercritical equations.
Yeah. Yeah. So basically here, I mean, we have initial data which was not covered by supercritical regime in the sense of Sobolev, but here we can consider that.
Any other questions?
You know about the Wiener measure in quantum mechanics, right? Have you?
Wiener measure? No.
Anyway, then no. Sorry. Yeah. Then never mind. Yeah. Okay.
Is there a larger class of equations to which your techniques could apply, or I mean, does it tend to be? I mean, I know this in the subject, like a lot of it is studying a specific equation.
Okay.
But yeah, I'm just wondering.
No. This will be for the Schrodinger equation, I guess. For other equations, up to local well-posedness, yes. But to get a global well-posedness, I'm not sure. Global well-posedness, I don't think this techniques will apply for the other equations. Up to local, I think we have just using the fixed point argument and the estimates for the nonlinearity. So up to local, we can handle many equations. For instance, for the wave equation, also we have a local well-posedness. But this technique will not apply for if you want to get a global existence for the wave equation, let's say.
Can you say a little bit more about what specific aspect of this equation you needed for the global existence case?
Because we need, first of all, we need global existence in the L2, and we also have for the Schrodinger equation, we have a conservation of in the sense of L2 norm.
Right.
And basically that help us, and the Strichartz estimate, and these two basically quantity help us to eventually to conclude that the growth term here in the case of solution of the Hartree equation will remain bounded. So that is the main key step.
But your arguments or the style of arguments wouldn't work for KDV? I still have an
KDV,
L2
I haven't tried, but I'm not my feeling is I don't think we will have that. I mean, local existence we get, that's for sure.
Yeah, I agree with that. I agree with that. But in KDV also I have an L2 global quantity. L2 norm is globally conserved, and the free part is also unitary. It's K cubed, but
here, see, for the KDV, we have basically Fourier multiplier will be xi cube, right?
Yeah.
Xi cube. So here one issue is here we have the free part we can handle up to alpha between 0 and 2.
Right. Okay.
So for alpha greater than 2, we have some loss of regularity. I mean, we have MPQ to MPQ, but we don't have exactly MPQ to MPQ.
Okay, that's okay. That's what.
So that might create a problem for KDV. I don't know.
Okay. If there are no further questions, we'll end this session. Okay. Thank you very much. Thank you, Divyang.
Thank you so much.
Thank you.